All right, so separately, we have talked about the rational numbers, and then we talked about the irrational numbers. And when you take all of the rational numbers, meaning the fractions or the decimals that either repeat or terminate, and the irrational numbers, which are the decimals that don't repeat and don't terminate, when you join those together, you get what's called the real numbers. These are the numbers that you use all the time in everyday life, in every situation. So just want to remind you of the different number classifications that there are. We talked about natural numbers. Natural numbers start with the number 1 and go 2, 3, 4, 5, 6, 7, 8. They just keep increasing by 1. The whole numbers, the only difference between the natural numbers and the whole numbers is whole numbers have the number 0, okay, in them. Integers are the whole numbers and then the negatives of the whole numbers. Again, no decimals, no fractions, no nothing. The rational numbers, like we said two sections ago, the rational numbers are any fraction, meaning any number that can be written as a decimal that repeats or terminates. And then the irrational numbers. We talked about pi, we talked about square roots that do not have a perfect square root, and decimals that don't repeat and don't terminate. So what we're going to do first is we're just going to get used to the different classifications. And here is a set of a few numbers. I've got -7, -3/4, I've got 0, I've got 0.6 repeating, square root of 5, I've got pi, I've got 7.3, I got the square root of 81. And we're just going to see what the different numbers are. It's just an exercise on familiarity with the different number sets. So first thing I'm going to do is I'm just going to make sure each of these numbers is simplified. This fraction's reduced. That's simplified. The only one that's not simplified is the square root of 81. The square root of 81 is the same thing as 9. Okay. So the natural numbers, which of these are natural numbers? Well, if you have to look up at the chart on your page, go ahead. The natural numbers start with 1 and increase by 1 unit. And so since they start at 1 and increase by 1 unit, the only natural number here is the number 9. Whole numbers start with the number 0 and increase 1 at a time. So now I have 2 whole numbers. I've got the number 0, I've got the number 9. So I'm going to write 0 and 9. Integers are the whole numbers and also the negatives. So I've got a -7, I've got 0, and I've got 9. Rational numbers are anything that can be written as a fraction or a decimal that repeats or terminates. So -7 is a rational number because I can write it as -7/1. -3/4, that is very clearly a fraction. 0 is a rational number, 0/5. I've got 0.6 repeating. That is a decimal that repeats. Now, square root of 5 is not rational. It can't be simplified. Pi is not rational. 7.3, that decimal terminates. So yes. And then 9. 9 can be written as 9/1. All those are rational numbers. There are 2 examples of irrational numbers in that set. We've got the square root of 5 and we've got pi. And then real numbers. Now, I'm not going to take the time to write this down. I'm just going to say all of them. All of them are real numbers because real numbers are anything that is rational or anything that is irrational. So I want you to please flip the page, and on at the top of the next page, there is another example just like that. Pause the video and identify what type each number is. Okay, we're back. And so the only number here that needs to be simplified, again, is the square root of 9. The square root of 9 is just 3. So we can go through each of these. Now, another way you could do this is you could just, well, I'm just going to do it the way I did the previous problem. So natural numbers. The natural numbers start with 1 and go by ones. The only natural number here is 3. Whole numbers are the natural numbers with also 0. So I've got 0 there and 3. Integers are the whole numbers and also their negatives. So I've got -9 and 0 and 3. Rational numbers are anything that can be written as a fraction or a decimal that terminates or repeats. So I've got the -9. Negative 1.3, that is a terminating decimal, so I'll write that one down. We've got 0. 0.75 with the bar over it, that is repeating, so that is a rational number. 3 is a rational number. I can write it as 3 over 1. Square root of 10, that can't be simplified, so that's going to be irrational. So I'll write that down right now since we're here. And then 9.57, that is a terminating decimal. And then square root of 41, again, can't be simplified, so it is an irrational number. What are the real numbers? Again, all of them. Now, the real numbers have some interesting properties that we take advantage of without really knowing, when we're going about our day-to-day activities. So we're just gonna real quick talk about these different properties and then end with kind of a fun little problem on a different type of way to use the real numbers. So the first type of properties are what's called the commutative properties. The commutative properties, to commute, when you use the word commute, to commute means to move. So the commutative properties deal with movement, and there are two commutative properties for the real numbers. There's the commutative property of addition, and there's the commutative property of multiplication. And you've probably seen these before. Maybe something will trigger in your mind when you see this and say, I remember seeing this. For addition, if I take two numbers like a plus b, then all that means is that's the same thing as b plus a. What that means is when you go to the grocery store, it doesn't matter what order you add your lettuce and your Coca-Cola, or your Coca-Cola and the lettuce, you're going to get the same amount to have to pay for your grocery bill. Same thing's true for multiplication. If you take a times b, it's the same thing as b times a. If I multiply 3 times 5, that's the same thing as 5 times 3. Those are the commutative properties. The next properties are called the associative properties. The associative, to be associated with something, means that you're grouped with it. So the associative properties have to deal with how things are grouped. Again, there are two associative properties, one for addition and one for multiplication. What the associative property says is if I have a plus b grouped together and I've got another one outside plus c, then that doesn't matter where the grouping is. What I can do, I'm going to keep the order of these things the same. It's going to be A, B, C. But what I'm going to do is I'm going to change the grouping. So now instead of the A and the B being inside the parentheses, it's going to be the A plus and then B plus C. So again, notice I've not changed the order. What I've changed is the grouping. And what that says is it doesn't matter the grouping when you're adding. You can add things in any order. And then the same thing's true of multiplication. If I have a times b times c, then that is the same thing as a times b times c. Again, these are things that you take advantage of in regular everyday life without thinking of, and it's a good thing because it would be hard to have to worry about what order to add things in or what order to multiply if you wanted to get the same thing every time. So my next example says, what operations on integers are commutative and associative? Well, I've already told you that it's addition and multiplication, but let me show you this by what is not commutative, and I'll just do commutative for lack of a better thing. So what is not commutative? Well, let's think about addition, or excuse me, let's think about subtraction. Let's say I have 5 minus 3. What is 5 minus 3? Your calculator will tell you that's 2. Let's reverse it. What is 3 minus 5? 3 minus 5 is negative 2. Subtraction is not commutative. The same thing would be true of addition. And the same thing is true for grouping. The not associative. So let's say we have 9 minus 5 and then minus 2. 9 minus 5 is 4, and 4 minus 2 is 2. Now let's say we change the grouping. 5 minus 2, that is 3. And 9 minus 3 is 6. So again, it's not associative. So subtraction is not a commutative and not associative property. Addition and multiplication are the only properties that are associative and commutative. Now, you probably remember this one from some algebra course that you took along the way, the distributive property. This distributive property says if you have something outside and you either have adding or subtracting on the inside, okay, I'll do this with both. Then the way to get rid of the parentheses is to do this thing called distributing. I could take the A times the B, get AB, and then the A times the C and get AC. Same thing's true for subtraction. A times the B is AB, and then A times the negative C is negative AC. And now you no longer have any parentheses, and you have a different expression. So for instance, if I have something like 5 times 6 plus 8, well, with numbers, we can do this 2 ways to see that it's true. First, I can do order of operations. 6 plus 8 is 14. And 5 times 14 is 70. Or I can distribute. 5 times 6 is 30. 5 times 8 is 40. And 30 plus 40 is 70. And you can see that the distributive property holds for those numbers. So again, I'm probably just reminding you of something that you've seen before, but we're just going through and talking about the properties of numbers. Now, here's one that you probably haven't seen or you're unfamiliar with, what's called the closure property of real numbers. And so what this says is if an operation is performed on any 2 elements of a set, and the result is an element in the set, then that set is closed under the operation. So here's an example, because I know that that's kind of a little bit of a goofy definition. Are the whole numbers closed under addition? So what this means is if I take the whole numbers and I add any 2 whole numbers, do I always get a whole number, or is there a chance of getting something else? So remember, the whole numbers start with 0 and go 1, 2, 3, 4, 5, 6, 7. They increase by 1s. So let's pick a couple whole numbers. So let's pick 5 plus 9. 5 is a whole number. 9 is a whole number. What do I get there? 5 plus 9 is 14. That's another whole number. Let's take 6 plus 3. 6 is a whole number. 3 is a whole number. I get 6 plus 3. That's 9. And so every time I pick whole numbers, the result is always a whole number. And so what that means is the whole numbers are closed under addition. Are the whole numbers closed? Yes. Now you might be thinking, okay, that seems fairly reasonable. What would it mean to not be closed? Well, here's what I would like you to do. Exercise 2. I'm going to tell you right now, are the whole numbers closed under subtraction? The answer is no. Find me an example of taking 2 whole numbers and subtracting them that gives you something that's not a whole number. And remember, the whole numbers start with 0, and then they increase by 1s forever. So find 2 whole numbers, pause the video, find 2 whole numbers that you can subtract that are not a whole number. All right, so hopefully you have taken the time to think about that. Remember, that's what it means to learn, is to think and to process and meditate on these things. So are the whole numbers closed under subtraction? Well, let's see. I take 2, that's a whole number, minus 10, that's a whole number. 2 minus 10 is negative 8. Negative 8 is not a whole number. It's an integer. So are the whole numbers closed under subtraction? No, because there is a possibility that when I subtract 2 whole numbers, I get something that is not in the set. So exercise 3, are the integers closed under subtraction? Well, we kind of just answered that question, but I'm going to give you a moment, go ahead and pause the video, pick some examples of integers and subtract them, and then tell me what you think. Do you think they're going to be closed, or do you think they're not going to be closed? All right, so just some examples. So 2 minus 10. 2 is an integer, minus 10 is an integer. 2 minus 10 is -8. That's an integer. -4. -4 minus 6. -4 minus 6 is -10. That's an integer. 14 minus 3. 14 is an integer. 3 is an integer. That's 11. So are the integers closed under subtraction? It sure appears that anytime I take two integers, I always get another integer. So yes, we would say that that set of numbers is closed under subtraction. All right. The next thing, so we've talked about the commutative properties, the associative properties, the distributive property, the closure property. There's just two more, and I know that's a lot of properties. The identity. What does it mean for something to be an identity? Given an element of a set, an identity is an element that produces the given element when the operation is performed. Okay, I know that's a little bit of a goofy definition. I'm just giving you a second to write those words down, and then we're going to think through a couple of examples so you can understand what the identity is. So example 4, what's the identity for integers under addition? So this means what element, when I add it to any integer, gives me that integer. So for instance, here's an example. Let's say we start off with 14. 14 plus what gives me 14? When I start with 14, what do I add to it so that I get the result, the identical result of 14? And I'm hoping you're saying 0. 14 plus 0 is 14. Let's try again. -6. -6 plus what is going to give me the identical result of -6? Well, that's 0. And so what is the identity for integers under addition? 0 is the additive identity. So pause your video, do exercise 4. What's the identity for integers under multiplication? Okay, so again, let's pick an example. 9. 9 times what is going to give you 9? Well, 9 times 1 gives you the identical value of 9. How about -16? -16 times what gives you -16? Well, again, that's 1. So what's the identity? What gives you the identical thing for the integers under multiplication? The number 1 does. Okay, so we've just identified the identity for both addition and for multiplication. Okay, the last of the properties, the inverse properties. Two elements in a set are inverses if the operation is performed and the result is the identity element. Does every integer have an inverse under multiplication? Well, here's a question for you. 5 times what would give you 1? That's the identity. 5 times what would give you 5? Or excuse me, 5 times what would give you 1? Okay, and hopefully you're playing around with this. You're thinking, oh, well, 1/5. 1/5 of 5 is 1. Well, here's the problem. That indeed is the inverse, but the problem is that this is not an integer. It's a rational number. So the rational numbers would have inverses, but integers do not under multiplication. Try this one. Does every integer have an inverse under addition? Remember, the identity for addition is 0. So does every integer have an inverse under addition? Well, let's see. Let's see 8. 8 plus what is equal to 0? Well, hopefully you said, oh, 8 plus -8 is 0. Oh, and that is an integer. So does every integer have an inverse? Something that when you add it up gives you the identity? Then the answer to that is yes. So it depends on the set of the number. The set of numbers, it depends on the operation. All right, so that is a really super quick overview of the operations. And so what we're going to do is kind of a little bit more of an interesting example than going through the whole numbers and the integers and the rational numbers. We're going to talk about clock addition. So I know hopefully you're familiar with reading a clock, but this clock is just is circular. So we've got some circular arithmetic. So first thing, what are the elements of this set? Well, look on the clock. The elements are just going to be the things that I'm working with. They're going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now we're not talking about the whole numbers, which are infinite, and the integers, which are infinite. We're talking about a finite set of numbers. So this makes for a little bit more interesting way to talk about the properties of numbers. So the elements of the set are that. So let's do some examples of clock addition. Okay, and we can use the clock. Let's say, okay, this is nice and straightforward. Let's say it's 2 o'clock and we go 3 hours later. Okay, well, here we're at 2 o'clock. We go 3 hours later. That's 1, 2, 3. We're at 5 o'clock. Okay, that's pretty straightforward. We would have probably guessed that anyway. Let's say this. Let's say it's 6 o'clock and we go 10 hours. Okay, well, here we're at 6 o'clock. Let's go 10 hours. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We end up at 4 because we're going around in a circle. I'm going to write a couple other examples. And what I just want you to do is use the clock to count off what the results are going to be. So just a couple of quick examples for you. Let's say that you have 8 plus 7. What's 8 plus 7 on our clock arithmetic? What is 4 plus 11? What's that equal to? And then what is 1 plus 12? I'm going to pause your video and go ahead and do those 3 problems, please. All right, welcome back. 8 plus 7, here I am at 8 o'clock, and I'm going to go 7. So 1, 2, 3, 4, 5, 6, 7. 8 plus 7 is 3 o'clock. 4 plus 11, here I'm at 4, so I go to 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 3. And then 1 plus 12. So I'm at 1 and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm back at 1. I go all the way around. So what I've done for you right below is I've just made a table of all the possibilities. So the way you read this table is I've got 1 plus 2. 1 plus 2 is going to give me a value of 3. And let's verify. 8 plus 7 you said is 3. So here's 8 plus 7. 8 plus 7 is right here. It is 3. 1 plus 12. So 1 plus 12 is equal to 1. That's how to read the table. And so here's just a few questions regarding the properties of numbers and looking at this clock addition under a 12-hour system. So we're going to apply the properties of real numbers to this clock addition. So first thing is, how can you tell the set 1, 2, 3, 4, 5 through 12 is closed for clock addition? Well, let's look in the body. Remember, an operation is closed if I take any 2 elements. So I take an element here on this side, and I take an element here up here, and I combine them, and I get an element of the set. So look in the body. Do I get any other numbers except for 1 through 12? Look pretty careful. Is there a 13? Is there a 19? Is there a -6? And when you look through here, you see that all I have are 1s through 12. So how can you tell that it is closed? It's closed because all of the results are 1, 2, 3, 4, 5, and I'm going to use an ellipsis all the way to 12. You don't get anything else. What we're going to do next is we're going to verify the following example of the associative property. And you can use the table, or you can just go ahead and use the clock and do it yourself. But okay, let's see. Does the associative property hold? Does it matter how I group? So 2 plus 3, when I go to my clock, 2 plus 3 is 5. And then 5 plus 10, okay, you can use the table or use the clock. Here is 5 plus 10 is equal to 3. Well, if the associative property works, then I should get 3 the other way. So here I've got 2 plus 3 plus 10. Well, go up here, 3 plus 10 is equal to 1. And 2 plus 1 is 3. So we got the same thing no matter how we grouped it. Looking at the table, what's the identity element? What is the element that every time I add it, I get the thing that I started with? So let's look at this. Here's the number 4. What do I add to the number 4 so that the result is 4? Well, let's go across. When do I see the result of 4? All the way at the end over here. And that is when I add it to 12. Okay, well, let's try again. Here's 9. What is it that I add that gives me the identical result of 9? Well, let's look. 9, which kind of makes sense. When I start at 4, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I go one orbit all around the clock. Same thing with 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I go one full orbit. Excuse me. So what that means is the identity element, the element that produces the identical thing, is 12. Let me put that in parentheses. The element that produces the identical thing. What's the inverse of each element? Okay, so what we're going to do is we're going to pick, remember, an inverse is the two things that you combine in order to get the identity. So let me come right here. We're going to do the work right below this. So what's the inverse of 1? 1 plus what gives me 12? And you can look up at the table. 1 plus 11 gives me a result of 12. Excuse me, it produces the identity. 2 plus what gives me the identity of 12? Well, that's going to be 10. 3 plus 9. 4 plus 8. And you can see how this is working. 5 plus 7. And then 6 plus 6. Each of those things are the inverses of each other. And then very last, pick 2 examples to verify the commutative property. So let's see. Let's see, I'm just going to do one example just for space sake. Let's see, does 9 plus 10, is that the same thing as 10 plus 9? Okay. Well, 9 plus 10 produces 7. And 10 plus 9 also produces 7. That's the commutative property. So here's what you're going to do. This is the last thing for this section. We're going to flip the page. And what I've done is I've changed the clock. Instead of going 1 through 12, it goes 0 through 5. And I'm going to give you, well, you're going to pause and take as much time as you need. But here's what you're going to do. You are going to identify the elements of the set. That's just what's on the clock. That should be pretty straightforward. I want you then to fill in the table below for the 6-hour clock. Okay, so you're going to go, what's 0 plus 0? What's 3 plus 5, etc. Then you're going to answer the same questions that we just answered about the 12-hour clock. So go ahead and pause the video, do that, and then when you are ready to compare notes, unpause the video. All right, so here we go. What are the elements of the set? The elements of the set are 0, 1, 2, 3, 4, and 5. Now we're going to fill in the addition table with this clock. So 0 plus 0, if I'm at 0 and I add nothing, it's 0. 0 plus 1 is 1. 0 plus 2 is 2, 3, 4, 5. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. And then 1 plus 5. Now 1 plus 5 is not 6. 1 plus 5, 1, 2, 3, 4, 5 is 0. All right, 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, and then 2 plus 4, so 2, 1, 2, 3, 4 is 0, and then 2 plus 5, 1, 2, 3, 4, 5 ends up at 1. 3 plus 0 is 3, 3 plus 1 is 4, 3 plus 2 is 5, 3 plus 3, so I'm at 3, and I go 1, 2, 3, that takes me to 0. 3 plus 4, 1, 2, 3, 4, takes me to 1. And then 3 plus 5, 1, 2, 3, 4, 5, takes me to 2. 4 plus 0 is 4, 4 plus 1 is 5, 4 plus 2, so I'm at 4, 1, 2, takes me to 0. 4 plus 3, 1, 2, 3, takes me to 1. 4 plus 4, 1, 2, 3, 4, takes me to 2. And then 4 plus 5, 1, 2, 3, 4, 5, takes me to 3. Last but not least, 5 plus 0 is 5. 5 plus 1 is 0. 5 plus 2, 1, 2 is 1. 5 plus 3, 1, 2, 3 is 2. 5 plus 4, 1, 2, 3, 4 is 3. And then 5 plus 5, 1, 2, 3, 4, 5 is 4. And there's my table filled in. That's my addition table for this 6-hour clock system. So apply the properties. How do you tell if the set is closed under addition? Well, because you only get the elements. This right here is the associative property. So with the associative property, 3 plus 4. So if I'm at 3 and I add 4, 1, 2, 3, 4, that is 1. And 1 plus 2 is 3. And then over here, 4 plus 2 is 1, 2, that's 0. And 3 plus 0 is 3. And so we verified the associative property. The identity element. What is the element that when I add it to everything, I get the identical thing? So just pick an example. Let's say 4. What do I add to 4 in order to get 4? 0. So the identity element on this one is 0. An inverse for each element. So what for each element do I add to it to get 0? So 0 plus itself gives you 0. 1 plus 5 on my table gives me 0. 2 plus 4 gives me 0. And then 3 plus 3 gives me 0. And then pick 2 examples to verify the commutative property. I'll do one, but it's easy to verify. So let's just say I have 3 plus 5 and 5 plus 3. When I do 3 plus 5, 3 plus 5 is 2. And then 5 plus 3, 5 plus 3 is 2. And so you get the same thing either way. So that finite set is just a novel way in order to review quickly the properties of real numbers. So I hope that was fun and interesting.